So let's go for the first talk, which is metal additive manufacturing, current challenges and opportunities. This talk will be delivered by Dr. RVS Prasad. Dr. RVS Prasad has been working as a research and development associate at Indian Institute of Science, Bangalore. Prior to this, he was working with General Electric. In India, we call it a GE India. And before that, he spent quite a lot of time in research and development as a visiting scientist at Korea Institute of Science and Technology in South Korea. So Dr. Prasad earned his master's from ITBHU, Banaras Hindu University in Metallurgy and Material Science, which is thereafter he did his doctoral studies at Indian Institute of Technology, Madras, again in Metallurgy and Material Science. So he has about 39 publications out of his PhD, postdoctoral and other research activities, and about 4 US plus European patents on his name. So without much delay, I welcome Dr. RVS Prasad to deliver his talk.
Thank you, Dr. Venu, for a nice overview and introduction. I'm really thankful. Actually, I'm very thankful to you and Dr. Parashar for inviting me for this talk. And at the same time, I also thankful to KIT for organizing this particular, manufacturing related, technologies and bringing all the people together. So without further delay, I just would like to start my presentation. Hope everybody can view my screen.
Yeah, we can view your screen. Put it in full screen mode.
Yeah. So it's. I hope everybody can.
Yeah, it's clear now. Go ahead.
Yeah. So today I would like to brief about metal additive manufacturing, which is one of the interesting area currently. A lot of research and development is going on. So I will be mostly discussing on direct energy deposition and materials related issues and challenges in this particular field. So today's my agenda will be the introduction about this 3D printing, and then what is this particular additive manufacturing, functional principles and advantages, disadvantages, applications, and AM processes and direct energy deposition, more specific, and then materials for AM and current issues and challenges, and what are the particular gaps and needs and research directions in this particular area. And then finally, the talk is open for the questions and discussion. So you can see this particular slide will gives you a history of 3D printing, which is started back in 1980s with the first documented use of 3D printing. So it basically starts with stereolithography, that is the initial stages of this 3D printing. And then, slowly over this 2-3 decades, it emerged into a much, versatile field, and which can be a lot of applications. And also, it's already into the manufacturing, particularly in Europe and US. Most of the industries already implemented this particular technology. Like if you consider General Electric, they have already like around 300 components in their aircraft engine. So that is the the brief introduction about this process. Like there is a lot of scope and potential for this particular area. So basically this is nothing but joining of the old process welding metallurgy. It's nothing but a kind of welding only, but however it's you can call it as a micro welding. So it will be kind of making materials, objects from 3-dimensional model data. Usually you can give a data in the form of 3D drawing, and then you can get it that in shape of the final component. So that's why we will call it or term it as a 3D printing. And then you can manufacture any components, no limitations with respect to geometry or tools. and it's basically uses a additive processes. And then this also can be a lot of conventional components also can be modified into different design. You can also eliminate or reduce some of the weight, and you can redesign and print. So that is the flexibility having this process, because in other processes what happens is you have to design, and then intricate shapes and all, you have to machine it, and sometimes it's very difficult to do the machining in the interior locations which unable to reach. However, in this case, you can directly give the 3D drawing so that you can print layer by layer. So you have a flexibility of printing a complex components. So that is one advantage this process is having. And also it is very much like most of the processes, conventional manufacturing processes are subtractive. So you have to start with a billet or a bloom initially, and then you have to machine it into different shapes, and then you can arrive at the final product, which requires a lot of traditional processes. However, in this case what happens is you can directly get the near net shape component by using this particular process. So, as I mentioned, this particular functional principle involves, basically four different steps. Basically you have a CAD file is required, and then you have to made it into STL format, which is nothing but made your design into different layers, like called it as a slicing, and then feed that file or a programming codes to the machine, and then you will end up with a final 3D part which you have given. However, only thing is you can get the final component by layer addition. So basically here what happens is the system starts by applying a thin layer of powder material to the building platform, and a powerful laser beam then fuses the powder at exactly the points defined by the computer generated component design data. And then the platform is lowered to another layer, and then powder is again applied. So once again, the material is fused so as to bond with the layer below the predefined layer. So you have, the predetermined design in such a way the laser beam moves according to the design given by you, and then it can be printed layer by layer and adds the layer by layer. So as I mentioned, this particular process having a lot of freedom to design, and it is a complexity free and a potential elimination of tooling, and a lightweight design. It eliminates the lot of production steps, unlike a conventional manufacturing. But however, this process also having a lot of disadvantages, because it takes a lot of time, like a very slow build rates. So current availability of the 3D printing machines, sometimes some components you may need 48 hours and 72 hours, depends on the volume of your component. And at the same time, the production costs are high because the input material is in the form of a powder, and again which is very expensive, depends on the material. Sometimes if you are going for a complex materials and alloys like nickel based super alloys or a titanium based alloys, then the cost will be considerably high. And then you also need to a lot of effort is required to application and design, and sometimes it's a discontinuous production process, because it's a mostly the 3D printing is a batch type of process. You need to get the design, and then you have to do slicing and all those things. And at the same time, the component size at the moment is limited because it depends on the bed size or the machine size of the AM process. So unlike in foundry or a forging, you can cast a huge components. For example, sometimes this forging process and all, the machine beds and all very huge. It will be in the length and the breadth of meters. So that kind of component, still the conventional manufacturing having the upper hand. So when it comes to applications, it is not limited. This process can be either it can be automotive or aerospace or a biomedical and general engineering and many others. So it is having a wide variety of fields in terms of application. Even biomedical having a lot of potential for this field, because you can do like implants, bone implants, and heart stents. So a lot of opportunities and possibilities are there for this particular technology. So I will be just briefing about the most AM technologies with respect to metallic materials, which is the primary interest for me, as well as the DED and other processes are mostly metal additive. So with respect to metal additive manufacturing, there are divided into powder bed fusion and power preform fabrication, binder jetting, and sheet metal lamination. These are the four different processes classified, and they can be further classified into selective laser melting, selective electron beam melting, and then in DED there are electron beam deposition, that is wire method, like by using the wire as a raw material. And similarly, laser deposition, there are two different varieties. One is powder and wire method, and also in preform fabrication there is a plasma wire. So this is with respect to DED. And then binder jetting, which is nothing but kind of powder metallurgy. It's already available. It's a conventionally available lot of tools and all which will be manufactured by powder metallurgy. So in this process, initially the binder will be used to print the 3D print component, and then they will be going for sintering, and then you will end up with the final shape. And then there is a sheet metal lamination. So now, as per my agenda of the talk, I will be more going to more details into the direct energy deposition. So if you consider process parameters in additive manufacturing, so there are direct energy deposition versus laser powder bed fusion. So here in direct energy deposition, laser power, laser beam spot size, powder or a wide feed rate, scanning speed, carrier gas flow rate, and layer dimensions. So these are very important. At the same time, when it comes to laser powder bed fusion, there is a laser power, laser beam spot size, scanning speed by velocity, and hatch spacing, and layer thickness. So these are the some of the important process parameters. And you can see on the right hand side, you have a laser and a scanner, and you can also see how the machine functions. So you have two pistons simultaneously. One is going up and another is moving down. So in powder bed fusion, once the part is printed one layer, the RAM moves down so that the other side will goes up and pushes the powder layer with the help of a powder roller. So then it will be a layer of powder will be formed, and then the laser beam comes and melts the required according to the 3D design which you have given as an input. And then the final component. So layer by layer, it will print, and then you will end up with the final component. When it comes to DED, so DED will have a significant applications in actual industry, because it's more industrial applications with respect to DED, such as you can do a lot of repair and refurbishment of the components. For example, if you consider a gas turbine, which is very expensive, lot of components in gas turbine are very expensive. So after a certain number of certain hours of intervals, like gas turbine usually comes after a number of cycles. Let's say, for example, if you consider a land-based gas turbine for power generation, which will have like 8,000 cycles. Once the cycles are completed, all the components will be dismantled and send it for the repair. So in the repair, what happens is usually in the old process, once the component is deteriorated, which cannot be suited for the next interval, so they will simply discard those components and they will replace with the new components. However, in the current scenario, by application of these new technologies, one can easily repair, because you have a 3D drawing of the actual component, and then you know which locations of that particular component is having issues, so that those areas you can build layer by layer and polish or grind it, so that you will end up with the component which is repaired but which looks like a new component. So that is one of the critical advantages with respect to direct energy deposition. So when it comes to process and microstructure of this particular direct energy deposition, it's very interesting with respect to the metallurgy involved in this. So if you consider this particular diagram, temperature versus time, you have a different layers, but at the same time, the layer one, if you consider at the initially the peak temperature is very high. However, it will going to come down as the other layers are building up. So similarly, once the second layer comes up, then the temperature will be different. And once the third layer comes, the peak temperature. So the peak temperatures increases as the number of peaks you are depositing on layer by layer. So when with respect to metallurgy, if you consider simple steel, you will have different zones when you are building up layer by layer. So the top layer will be in the liquid state because where you are melting the powder and depositing, and then there is a second layer which is intermediate level, which is in the austenitic zone region. And then the third layer will be, the layer between the second and third will be in the solid plus liquid zone, and then the bottom layer will be at the solid zone. So you will have a very interesting metallurgical sequence is happening as when you compare with the layer by layer. So it's very important. Once you finish this particular process, the heat treatment is a very important aspect with respect to this direct energy deposition. And then in direct energy deposition, also the melt pool dynamics are very important. For example, if you consider the surface tension and the Marconi effect, which is very critical. So you consider the dimensionless Marconi number can be determined by m equal to dou gamma by dou t, and dou t by dou x, and L square into divided by n alpha. So where the lot of things will come into picture, which is very critical for this particular DED. Like the gamma is the surface tension, and dou t by dou x is the temperature gradient, and the dermal diffusivity alpha, and L is the characteristic length, and then N is the viscosity of the melt pool. So all these physical properties will determine your melt pool dynamics. Say for example, if you consider your surface tension gradient is negative, then you will be having a melt pool which is wider, which is shown in the figure. And similarly, when the melt pool geometry is going to change when the surface tension gradient becomes positive. So as shown in the next figure B, when it is positive, then the melt pool will be shape and dynamics will be going to change. And similarly, when you have a positive and a negative, so initially it will be positive and then it becomes negative, then the melt pool will be very turbulent and you will have a different kind of pool is going to form. So in direct energy deposition, so these are like a lot of other forces also play into a role, like aerodynamic drag and buoyancy and electromagnetic and Lorentz forces may also influence your melt pool dynamics. So that is with respect to melt pool. And then the dilution also very important factor in case of direct energy deposition, because when you have a layer by layer is depositing, and if you are not having a very good dilution, then the bonding between the two layers are not at all possible. So for example, if you consider in this particular equation, D is equal to D by H plus D, so that this is the the melt pool height H, and D is nothing but the depth of the melt pool which go into the previous layer. So if it is usually people will consider 10 to 30% dilution is required for a proper banding between the two layers. At the same time, too much too much dilution is also not good or not very important. So usually one has to optimize a 10% to 30% dilution, which is very important and also required for a proper bounding between the two layers. So this is also a very important factor when you are considering direct energy deposition. So and then with respect to processing maps are very important, because when you are going for a direct energy deposition, there are two important factors which decides type of defects or type of phenomena which is happening in the your material. For example, the linear heat input, which is nothing but laser power divided by the scanning speed of the laser, and then powder feed rate, which is nothing but total mass of the powder, and the time T is the time to deposit the powders. So when you have a laser linear heat input versus powder feed rate, you will get a processing maps for this particular direct energy deposition. So when you have too much very high laser input and with very low powder feed rate, you will be ending up with a keyholing kind of phenomena, which is also defect. And at the same time, when you are having very high powder feed rate and low heat input, then you will end up with a lack of fusion. And at the same time, you will also end up with a mid porosity zone where you will have a very large linear heat input is very high at powder feed rate, at optimum powder feed rate. You will also end up with a mid porosity zone. However, if you consider different materials, you can see the in the map different colors for the with respect to different materials. You will have a not a single point. You will have a range of area where you will get a better DED or a good dilution and without any defects. However, those areas, for example, if you consider iron 718 alloy in this blue region, you will have a large window for this particular alloy. So you have to choose this particular window with respect to process parameters, but at the same time, you have to get the samples from this window and get it tested for all the mechanical properties, and you can arrive at the what is the best in this window where you can get the best properties. So in a way, you can decide the best possible process parameters where you can optimize to get the final properties with very good, mechanical properties. So that is the thing, and you can also see in the beside picture how much dilution is happening with respect to each alloy, and there are number of alloys which have people have been tried and generated this processing map. So this is a very important key aspect of any process to proceed with any new material or a new alloy development. So now I completed the more detail into DED. So I will be going to touch upon different materials required for 3D printing. So particularly I will be focusing mostly on the metals and alloys. So there are different materials like steels, in which steels also there are maraging steel, 174PH, and super alloys, titanium based alloys, and aluminum magnesium alloys. So these are the typical alloys which can be used for metals. And then which is for plastics, there are different materials and other materials like biological and bone applications like bio ink and bone materials. So I will be touching upon the alloy selection and design for this particular additive manufacturing process. So when you come to this materials selection, the important aspect is free energy versus temperature diagram. You can see the free energy versus temperature diagram where the liquid and solid will be different. Once the free energy of that particular phase becomes lower, at higher temperatures the liquid will be stable. At the same time, solid will be stable at lower temperatures from this particular free energy composition diagram. So this is very important aspect because when you're considering for a new alloy or a new material, the melting point will be varying with respect to different materials, which is, for example, the aluminum will be having around 650 and in that range, and the other alloys like steels and all will be at very high, like 1500 degrees and above. So when we are considering melting point and all those aspects will come into your laser beam density calculations and laser power calculations and your scan velocity. So not only that, for example, the reflectivity, a lot of physical properties like high reflectivity, high thermal conductivity, and the melting point. For example, if you consider aluminum, there is a oxide layer formation on the surface, like Al2O3 will form on the aluminum. So all these things should be considered when you are choosing for a new alloy. And then when you are developing even the laser absorption coefficient, for example, you have a different metals which is having a different laser absorption coefficient and wavelengths. So when, for example, copper, you need a very high laser input. And at the same time, for a mild steel or a stainless steel, where you don't need a very high laser input, laser energy. So it depends, for example, copper and aluminum will have a lot of high thermal conductivity. So it will quickly dissipate your heat so that you need a more and more laser input or a laser heat input. But other materials will have a low thermal conductivity. There it will behave differently. So at the same time, even if you see the following diagram for inconel based alloys, for example, the aluminum and titanium percentage in that particular alloy will play a significant role. When the aluminum and titanium content is lower, it is the weldability of these particular alloys like IN718 will be very good. However, when you are going for say in the same category of nickel-based super alloys like Li738, then it's very difficult to weld, because the percentage of aluminum titanium will vary and the weldability also going to differ. So in a way, this kind of alloy diagrams and processing maps will give a clear picture how to select a alloy for this 3D printing processes. So when it comes to defects in this particular field, you have a lot of challenges like porosity, which is very common in 3D printing, because for example, there are two different types of porosities. One is process induced porosity, that is which occurs the porosity during the process or a melting, and then there are a porosity which is powder induced porosity, like when the input material powder itself may have a porosity during the atomization process. So these two porosities will be different. So the selection of powder and characterization of powder is a very critical before feeding the powder into the 3D printing machine. So initial qualification and certification of the powder is very important aspect. At the same time, process induced porosity. So as I mentioned, you have a lot of unmetal powders, and like in the previous talk, Prasant clearly mentioned, if you have a satellite particles on your metallic particles, it may going to in the process it may leave as it is and are unable to melt those very fine powder particles. So those kind of possibilities are also there. And if you consider this particular diagram, laser power versus scan speed. So this is very important, diagram to determine, to arrive at a good functional parts. So here you can see three different zones. So when you have a scan speed versus laser power, when the power is very low and at lower scan speeds, you will be ending up with a lot of defects like as shown in the figure, which is unfused particles or unmelted zones. At the same time, if you have a significant laser power but a very low scan speed, you will end up with a gas porosities because of the rapid solidification nature of this process, which is very high cooling rates. Because of that, the gases will generate, and when it is going to escape from your liquid pool, it may trap in between, and you will end up with a gaseous porosity. And at the same time, when you have a very high laser power and scan speed, there is a phenomena called balling. That means it will just simply push the powder without proper melting. So you will end up with a balling kind of phenomena. So for example, in this case, it's a pure aluminum mixture. So people have done number of experiments. You can see like more than 40 experiments. However, they can only, you can see the green color images, which is, optimized process parameters with a particular laser power and scan speed, where you can able to end up with the good parameters. But out of this, you have to check which is the best mechanical properties and with better ductility and heat treatment optimization. Then you can end up with selecting those locations and freezing the process parameters. So maybe all these experiments may become waste, because you have to do, unless you do the optimization, you don't know what particular region is good for a particular material. So this experiment in case of the pure aluminum mixture. So you can see clearly, these are the, fusion errors in this zone, and where you have a lot of porosity in this particular zone. And however, you can see in this particular zone, you have a better quality parts will be getting. And Another challenge is residual stress. So this is also very important because when you are this rapid solidification nature of this particular process, like when you are building a component from the base plate, you have a different challenge. Like the base plate temperature and the building part will have a difference in the temperature. Then you will be ending up with a lot of residual stress in the build direction, that is Z direction. You can see in case of Z direction, you have a lot of residual stress, compressive residual stresses are induced. Whereas in the X and Y direction, you have not that much residual stress. And then these residual stresses also going to create a problem, because if you are not relieving the residual stresses and using the component for final application, then what happens is it may generate cracks or going to premature failure or is going to happen on the component. So that's why the residual stress determination is very important. So usually people will go for after 3D printing, they will go for a annealing heat treatment, where all the residual stresses will be eliminated or reduced, and then the component can be dispatched for the actual application. So in a broad generalities, see the like properties like stiffness, strength, hardness, ductility, fatigue, and toughness. So these are very important aspects of any component. So when you compare with the conventional processing, so you have a stiffness is more or less equal in case of AM parts, and strength is also as strong as or more than better stronger, and hardness also harder or better hardness. But here the challenge is ductility. So more in AM case, which is very less ductile compared to the conventionally manufactured parts. And more importantly, because aerospace related components like aerospace applications, the fatigue and creep are very important. So the fatigue and creep still in AM parts is not excellent or not achieved the like a conventional level of fatigue life or a creep life, because it's obviously these parts are having a porosity which becomes the problem for a fatigue and a creep kind of properties for aerospace application. And toughness is also less tough. So but people are trying to increase the ductility or reduce the porosity. People are going for a hot isostatic pressing, where you can eliminate or completely remove the porosity from your component, and then it becomes as solid as any conventional component. So still there is a lot of research is going in this direction to enhance the fatigue and the creep properties. Particularly those properties are weak in this case of additive manufacturing. So those can be improved by different techniques like hot isostatic pressing, where you can equally come up with properties like a conventional material. So this is the summary for my overall overview of this presentation. So you can see the key issues are porosity and residual stresses. These are the major key issues with respect to AM. And also this is, since it's a non-equilibrium and a very rapid solidification kind of process, you will end up with a multiple interfaces and boundaries, and alloy and composition design suitable for AM processing. So these are the some of the key issues, and the technical challenges like extremely localized temperature gradients and fast moving heat source, because the laser beam moves like a very high speed in case of 3D printing. So that will have a lot of implications when it comes to the actual application or properties. And dynamic gas solid liquid interactions, and fast heat mass and phase transformations, and laser radiation environments associated with this particular processing. So these are also again a lot of things need to be improved in this direction. And dynamic localized directional solidification, because the heat extraction rate is very high. So you have a possibility of a directional solidification, where in the solidification like a columnar and equiaxial, all those things are in this case mostly columnar or columnar dendritic kind of things are going to happen in this environment. However, this can be eliminated by heat treatment. You can make it more uniform. And the qualification and reliability of the products. So this is also very important with when it comes to manufacturing industry, because the reliability is a very important. And then post processing. So post processing also like a heat treatment and removal of the component from the base plate, which requires a lot of effort, like wire cutting and all those methods need to be improved. And then material properties, as I mentioned already, like fatigue and creep properties of these AM components very major challenge in this particular methodology. And the production rates and the robust process, like increased production rates and guarantee consistent production and material properties. So that is also very important, because nowadays lot of improvement is going in that particular direction. Like a quadra laser, 4 times. Earlier there is a single laser. Now 4 times you can build a component. For example, you are taking a 4 hours time. You can build the same component in 1 hour by using a quadra laser. So those kind of lot of improvements are happening. So with this, I would like to end my talk.
Thank you, Dr. Prasad. It's an excellent presentation. You took us from the basics of additive manufacturing to quite in detail studies of solidification phenomena and the welding or the liquid pool convection phenomena, and the challenges what we have today. Excellent presentation. Because we are running ahead of time, so 1 or 2 questions from the audience. There is one question. Magnesium metal base or calcium metal base additive best performance in automotive additive? Not quite sure what Mr. Patel means.
Yeah, I'm not very.
Chat box. Mr. Patel, could you rephrase your question, please?
Sir, he would like to ask, like, Mg metal base or calcium metal base, which give best performance in automotive additive?
So at the moment, automotive additive, mostly aluminum based alloys are people are trying, like aluminum silicon magnesium alloy, where it's similar to 6061 wrought alloy, where the aluminum is the matrix phase and the Mg to Si, which will evolve during the heat treatment, like solutionizing and aging, so that you will get the better strength and toughness. So particularly there is a lot of components in the automotive sector, which is by using aluminum silicon magnesium alloy. That is the prime alloy in the automotive sector currently people are using. But I don't know, I'm not sure about how, like magnesium, calcium, I have not heard anything with respect to that.
All right, thank you, Dr. Prasad. Thank you very much for an excellent presentation. With this, we will move to the next presentation.